technique. You guys, you guys know better than this photographical sort. Have you heard of Khan's algorithm? Okay, yeah. I hear a few guesses. Okay, we don't use Khan's algorithm here. Why? Khan's algorithm is for big graphs. I don't see like people using 10,000 dependencies. Like we don't need Khan's algorithm here. So you have to rebuild entire graph. Okay, next step we do is we sort the routes. You wrote all your code as a decorators and now it's trying to store. So currently we store it in hash map. Like actual servers, they store it in statistical radix tray, which we are implementing it in the next version of FastRAPI. But for now, all of them are in a hash map. This is a special hash map. Sorry, normal. It's called Papaya, and for each single thing, for get route, the path, and then it has a special route handler. This strap that you guys have seen before, it stores all of this information, all of this stuff. Okay, what is papaya? Not the fruit. So a bit deeper into this. Okay, how many of you guys know concurrency? Okay, I assume a lot of people know. You guys know reader writer log, right? So for people who don't know, reader is someone who constantly like you go to a library. Imagine a library where authors is also there, and they'll be constantly writing books. And Peters, as you'd be reading as they constantly updated. So how do you make sure that people get the latest versions? All the hash maps suffer from this issue called reader regular log contentation. And Papaya doesn't have it. I'll show you why in the later slides. Yes, it works very well on heavy workloads. And Papaya is a hash map, in case you guys don't know. There is no, you can never tell log here. I'll show you how later on. There's a concept called Swiss tables it used for cache locality. Any of you know what cache locality is? Okay, one or bit. Okay. I told there is no contentation. There is no concept of readers writers. So how would you update stuff? You consciously write and you consciously read. How does Papaya do it? I'll show you with a simple example. This is my item. This is my full hash map. Just imagine. Okay? That doesn't look like a hash map, but just imagine it's a hash map, okay? And you write something to it. That means add a new element to the hash map. So what Papaya does is it clones it somewhere and you add something, add a new element to it, and fact everywhere, SQL, Bluebeam, deployment, all of this stuff. But this is something Papaya uses it internally inside of hash map. I see. Cache locality. This is a very deep down Capella concept. So you guys know N1, N2, N3 registers? You guys know what a memory is? How many of you know what a memory is? How many of you know what registers are? Okay, yeah. As you all of you know. So I'll continue with a simple example, okay? And I want to go okay. My mom asked me to go grab a milk, okay? I go there, I grab the milk, I come back. And then she tells me again, based on true events, go get something else. And I go there and I get it again. Instead of all of them, my mom could have just told me, she should have gave me a list of items to get and I'd have gone and I could have gotten all of this. Now, what's the issue here? I go to the shop, I get it, and I come back. That is bad. What is good? If all the shops are nearby, I could just go there, get one item, go to the next shop, get the next item, go to the next shop, get it, next item. There's the same thing, there's the same concept we use in compilers called cache locality. So you store the data, which you most likely would use later on, very nearby, very closer to each other. That's cache locality. And there's a thing called Swiss tables. This is the relationship with Swiss tables that was made by Google to increase cache locality, and Papaya uses that. I won't go very deep into this. Okay. All of this is started during startup. So what happens? per every single depository way. How do we get this much speeds? One lakh speeds. How do we get 100K? Okay. First things first. It's a slash ut slash 123. It hits us reverse. So now what do we do? First thing, we lower papaya lookup. We'll see what is stored in a papaya. This, the type of request, the paths, and what route to follow. Okay. Now what? It looks up. It looks up the papaya, the hash map, and then gets the route. Okay. After you get the route, what do? This next optimization I'm doing is called a fast path. So people would usually go in normal way, but there's a better path so that people make. It's called a desired path, by the way. And fast path. What's a fast path? You don't have to do all of this stuff you don't have to do a lot of checks for a certain stuff. That's the reason in the start we store if a function is async or not. If you see here, we store if it's async or not, if it's fast path or not. We compute if it's an async, if it has path parameters. Because for a simple slash get request, a simple slash post request without any parameters, I don't have to keep on checking every single. I don't have to pass every single time, right? So I'll show how this works. So what's a fast path? If your function is not asynchronous and it doesn't have any dependencies, so it doesn't have to check it, the dependencies, all of this stuff, it's a fast path. This is the code I wrote. If it's not an async, and if its dependencies are empty, where it says fast path. Okay, if it's a fast path, then what do? You guys is pedantic, right? Yeah. So all the frameworks ever made before as a competitors to FastRAPI, right? None of them had any pedantic integration. And here I do pedantic integration. It's a very simple call to Python, which is done at the startup, and then you store all of them at the Rust site. So, okay. All of this nerdy stuff later. You check for pedantic. If pedantic exists, then you do validation. And then you extract all the parameters also. After you get all the parameters, you convert the result. So you just send it to Python to print them. So what I'm doing is I take stuff from Python. I do all my stuff from my Rust binary and I give it back to Python. Okay, I'll talk about this later. Oh wait, no, let's solve it right now. So what's the difference between this picture and this picture? Anyone? Yeah, response type, right? What's the response type here? JSON. After I added the JSON response, I mean, it's a very minor spike, but what's going on here? 47,000 requests, here 48,000 requests. This around like 500-ish requests per second, like increase. So very minor, but like this is a very small optimization we did in FastRAPI. How did it? What happened here? Okay, this is a bit deep. This goes on how instruction cycles work. For every single if call, they say jump if not equal to instruction call. So FastRAPI checks if you did not provide this JSON response, that is in this case. It needs to check something. It checks if it's a JSON. If this result is JSON. And then it checks it's a plain text. And then checks if it's a HTML. Or then it'll check if it's a redirect. After doing all of these checks, if it's probably not a JSON, if it's something like HTML, it'll take you some time. This is always the best practice to use. What is the response tag you're getting? This is do 4 checks, 4 instruction cycles, plus all of them passing work. You give the result type. Then what? So, I'll tell you in a simple way, okay? Here, if the difference between match and if performance wise, what do you think is fast? Match or switch in other languages, or if what is? Switch. Why? Like, can anyone explain why switch is better? Oh yeah, someone said here. Yeah, it has jump tables. So jump tables are like if it hash your response, if this is of this type, or every match statement, if it matches this, then you jump somewhere. If it matches this, you jump somewhere. It's like a hash, but think of it like a hash map, okay? Hash table. And here it's O of 4. Why 1, 2, 3, 4? It needs to do this. But here it's O of 1. Okay. That's this very minor optimization. Okay. This is the coolest part about Rust. I mean, except from all the other coolest parts, this is like one of my features that I really love. Inlining. This is what happens in other languages. You don't inline ever in like other languages unless you explicitly mention in a very few languages have this. You have a function for add. And the second thing I do is I add 10 or 20. For guys who don't know Rust, you just add function to add A and B and it'll return it. So you don't have to put data inside Rust, so you just return it. And here I'm adding 10 and 20. And I can just print the result in. Now what will happen? What will the compiler do after I run this? I have an add function, it will add 10 and 20 and resist it. Now the CPU will physically go to the add address location where the function is good, check it, and it'll come back again. This is without inlining. Every other language does it. But if we inline it, this is what happens. This is my add function, it has A plus B. And then I run add function with 10 or 20. Now if you see the difference between here and here, there's an add function here, but there's no function here. This is done during compilation level, not during runtime, it's during compilation. It doesn't have to call the function again. It pastes the entire function just from that place. This is called inliner. So when did we use inlining here? We use inlining in a response type, which I'll talk about it later. Okay. After all of this, your request is done, go operate. This is for fast paths. What about paths which are asynchronous and other stuff? This is like a novel path you go. Like if you're a novel person, you take a novel path, right? Then what? If you get a complicated request like this, /users /42 and status is active. What is the problem here? I mean, not a problem for SDE, but like if you're making a software and you have this, what's the problem here? This entire thing, I'll have it as a string. 42 is a string. Active is a string. So what do you do right now? You validate stuff. How do you validate? It's basically mentioned it in the path parameters. This okay, this is an int and it has a greater than value and this is a less than value. So this number can be greater than it should be greater than 0. It can be more than 100. Okay, you put this and it'll automatically get converted. And this is a Rust style. Pass it to IC is signed integer of 64-bit. You don't have to worry. I won't talk about this. So I did conversion. So it'll convert because it's strictly mentioned it's an integer. You just have to do this and it'll automatically pass it on the Rust side and will give it to you. And it's very fast. And it's very constraint validations that you do. You can just put greater than or less than whatever you want. Okay. Dependence. And the next part is literally dependencies. It'll check like which to execute first, then what. Okay. First, these two will get executed first. After these two, then this gets executed, then this gets executed, and this gets executed. If I want to do this, so and why did I do this first or not this? Wait, no. Because this doesn't depend on this. So it doesn't matter. I'll put it in my queue directly. And also this memoized or cached. So what happens is like you don't have to like keep calling for the same very parameters. The result, like all of this checks, you don't have to do this again and again. We have an option called use cache equals to true, which will like handle all the dependency issues for you to cache above. Now comes the final question: sync or asynchronous? So from here, you do first path is gone. You have a normal path. You're a normal. It's a normal path, and now let's choose the film. Sync was async. So what if it's a sync path? Everything runs on one spawn. I'll talk about this later, what spawn blocking is. It merges all the dependencies into keyword arguments. It calls the Python function, it returns the response. What's fun blocking here? There are two types of pools. In like almost a lot of languages, you have a blocking pool. Any language which has async, like and sync, asynchronous is your blocking pool. That means if I do something, others have to wait for it. I'm in a queue, I'm doing something, others have to wait. It's a blocking pool. And you can put any number of threads here. There's 100 people in a queue. So if it's of a show which gives like you started rid of a queue. And this like you can grow up to any number of threads. But what's the issue? You have to wait until you go inside the shop. That's your blocking pull. It literally blocked. No worker pull. Any cohesives here? Go line. Revolt. Okay. How many cohesives here? Okay. Okay, I see one or two over there. So worker pull, you guys have cores inside of your laptop. So what do? They use worker pools, literally make workers. Instead of you standing inside of a queue, I mean, even here there's a queue. So these are very fast pass. That means these don't block at all. I'll just see it and I'll return it. I'll just see it and I'll return it. This is task like this. So they must never wait. So there's fixed number of CPU cores and it does n is to n threads. My scheduler that is talked earlier, my scheduler will assign 100 workers, but my laptop only has like 24 cores, okay? So you can't put all of that in. So it uses MSHAME model to convert it from 100 to 24. It's very lightweight too. Okay. What if it's asynchronous? Okay. This is a fun part. I think there was no ASIC port for, at least for IoT. That's the thing I'm using to build this entire ecosystem. So it could not do ASIC things a year ago. But like last year, they released something for certain times. Now, what's the future? You guys know what promises are, right? You need JavaScript developers. You guys know what promises are, right? The promise is like, your crush will tell you, okay, I'll call you later. That's a promise. But here in Rust, we don't have promises. We have something called the futures. What's the difference between future and a promise? A future is just a lazy promise. That means it'll get executed only when you call it. Like only if my crush remembers it, she'll say, I'll call you later. That's my future. Okay. Now I'll await. This Python will send this and this to my Rust future. No, I'll await. I'm in Rust side. In Rust at least in Tokyo. Now I'll wait. I'll say, okay, I'll wait. Now, after it waits, and now it'll convert the results to Python. Okay, it'll await, it'll execute it, and now here the execution is the call that she actually called, and you convert to Python. Simple. Intern. It's not internship, by the way. This is a concept in Python and in Rust and Python too. So what happens is your Python stores it usually stores your all the strings inside of a heap. To avoid all this issue, it stores inside of a heap. Every single string has a specific address to it. But every single time we run it, it has to call all of the places again and again, which is bad. So what it does is save the pointer. Here hello is here ADC and DEF, but here it only show it in ADC. And the next thing it'll do is it'll just save the pointer as ADC. I'll just call the same thing again and again and again. This is what happens if you do inter. Not only confused with Python iterning. Python has two concepts, interning and iterning. Iterning is a completely different concept for caching all the variables. Then the iterning is different too. Okay. Now there's a security issue. In FastRAPI, there's a security issue. Now, if someone is sending a payload more than 1 GB, then what do? It has to pass through all of that. That means it'll crash. It goes out of memory error. So it crashes. So what do? So what is FastRAPI do to solve it? Okay. In FastRAPI, we don't solve it at all because FastRAPI doesn't solve it too. If FastRAPI doesn't solve it, FastRAPI doesn't solve it too. So technically, you have it in your reverse proxy Nginx. If you set up a reverse proxy, it will automatically handle it for you. I'll complete these small automatizations in a few minutes. So I'm using there should do a small vector. This is the optimization even you guys can use in your projects. Rust projects we're doing it. So if it's a vector and of type T and I'm allocating 4 elements, here you can store it. You store 3 variables inside this capacity, okay? But what if you go more than this? All of this is stored in stack, right? The stack is fast, keep it slow. If you go more than 4 elements, if you go input T, D and D, then what do? Then he store it in heap. This is what small vector does. Until a certain number of capacity stores in stack and then it'll go to heap. And then parking lot. Not be confused with the actual parking lot. You guys know what a mutex is? Who doesn't know mutex? I mean, okay, who knows mutex? What a mutex is? Okay, very few. Okay. I'll show you the very bad example, okay? You want to take a piss, okay? And someone is already in the washroom. So what do? They go into the washroom, they lock it. And then they'll do their work and then they'll unlock it. That's literally a mutex. And parking lot is much faster than mutex instead of Rust. I'll skip over this slides because we don't have much time. And the AK is also very simple to change from mutex. That's what you do. Oh, I also made a contribution for Papaya, which is still not accepted. I made it 9% faster by replacing all the mutex with parking lot. Okay. Next thing, profile guide optimization. So what it does is, it'll do all of this, inlining, branch predictions, code layered, all of this stuff, it'll do it by itself. So you don't have to worry about it. The PGO was recently added to, it was a big concept in Rust, but like it was recently added to Pio3 is the framework which I'm using to build this. So other optimizations that you can do to discuss about it. GI removal. All of this entire project wouldn't be possible without this. Python, before 3.12, it used to have something called as a GIL. I'll explain this in 2 minutes, okay? So, you have a list, two lists. You have list A and list B. And both of them you append 1 and 2. And while list A is running in thread A and list B is running in thread B. And before GIL was there, your thread A, your first thread A will acquire GIL. It'll now, yo bro, I'm gonna handle this list. Will say, bro, I'll handle list A. And the others will not even touch. Thread B will not even touch. Because why? It's handling list A. But list A and list B are not connected. So yet, it has to wait. List A executes first, then list B. First list A acquires the log. It's like a token. Okay, you go exile, you do all your work, and then you come back. And then list B, thread B does all the work. But after GIL, what happens is, since list A and list B are they're not same, and they have different Pi objects. I'll cover Pi objects in a second. It first logs this 12 objects. Bro, if I'm batching list A, no one else touches listing. I'll do its work. And thread B also says the same. If I touch list B, no one else touches list B also. This is what happened. Before, everything used to call your memory pool. Bro, thread A is with thread B won't do. But here right now, if thread A is doing for some object, nothing will do for that object. But they both can execute parallelly at the same time. Now reference costs. Okay, this is the reference cost. How many times is a variable has been used? Here, 1 time is used, 2 times, 3 times. And if we delete the entire, delete y, so this y is not this, so it's raised to 2. Number of times the variable has been used is called reference cost. This is a Python object. I won't go deep into this. We don't have time. So this is before GIL. This before GIL, you have a reference count, and after GIL, you have it